So far we looked at linear regulators or LDOs, where we know that your control signal is a analog signal VCTRL. The difference between switching regulator and linear regulator is that here the control is a duty cycle, which is basically a pulse width modulated signal, which regulates your output. So, it works on the principle of pulse width modulation or PWM. And this we already looked at that it offers higher efficiency. Across white V out over V range. Okay. Can buck, which is nothing but a step down, boost, step up, or invert, input power supply. Okay, which means if you have a switching regulator, and if this is your VDD and this is your V out, means V out could be less than VDD, V out could be greater than VDD, or V out could be less than 0, which is negative, or inverting. So, how does it work? So, let us say if I have this PWM signal with a period of, let us say, TSW, and I call this T on and this is T off. If you take the Fourier transform of this, how will it look like? Spectrum. What all components you will have? Yes, sine will have, but how will you plot it on frequency? If this is your frequency, and this is your amplitude, what is the first component it will have? It will have a DC component. So, let me draw. Okay. So your 1 over then and so on. So which one will be the significant? DC will be the, and rest of the harmonics will have a smaller component. So it may be like this. In fact, some of them might be more than the, so order even harmonics, if you look at, it's not necessary that it will keep decreasing, but it depends on your duty cycle actually. So the expression is not straightforward here when you take the Fourier transform of a triangular signal or any other, or the Fourier series when you look at it. So, and if it's a perfect square wave, then it will have only odd component, but if its duty cycle is not uniform, then it will have both odd and even. So what I am interested into, what output I would like to have? I want a DC, okay. So which means if I have a filter very low bandwidth filter which is a cutoff, okay, which means if this is your low pass filter, so if 3 dB cutoff of LPF is much less than 1 over TSW, then all harmonics are filtered out and we get only DC component at V out, okay, which means if this is your LPF, which will have something like this, this is your PWM signal and this is V out. So what you get here, so DC with very small ripple, okay. How do we implement this filter? And what, by the way, what is the DC component? V out equal to, so that will be the average value of that. So average of that will be T on over TSW multiplied by VDD, which is nothing but duty cycle times VDD. So how do we implement this filter? What could be the possible ways of implementing this filter? RC? Okay. Let's see. RC. If this RC time constant is much larger than TSW, okay. So this is your VDD This is your V out. Now I have a load here. What will be the drop here? I load into R, which means what is V out? VDD minus I load into R, and what else? D times basically, correct. So now let us say, what should be the value of this resistor? What should be the value of this resistor?
It will be much greater than TSW by C.
TSW?
By C.
No, but you are putting a load here, right? That is driving load. How can you make it? So let us say you put a 1 ohm, you put 1 amp you draw, 1 volt is directly dropped at resistor output. If you keep increasing that R, you will not get anything at the output. Everything will get dropped at a resistor. So if now let's take an example. So let's say your TSW is 1 microsecond. So which means R should be much smaller to supply higher load current. So let's say R you make 100 milliohm. I load is 1 amp, so you will drop only 100 millivolt, which is okay. Now see, let us say you want RC time constant, let us say I want 10 times of TSW. Let us calculate the value of C. 10 into 1 micro over 0.1. What is this value? 100 microfarad. And even this 10 times I am considering, it is on the lower side actually. Usually you would like to have time constant even much larger, so that your ripple can further reduce. So 100 microfarad is not a small cap, it is a huge cap actually. So it is not feasible to implement with RC, because it will require a very large cap, which is not practical actually. So what else can we do? So RC filter is not practical due to large C. Okay. So what we do? So we use LC filter. So ideally L is lossless, so you will not drop anything when you draw the load. I load, so V out equal to D times VDD. Okay. So there are two advantages here. One is reduced losses, okay, and for the same ripple, your value of C required will be much smaller because it's a second order filter. Okay, so you get minus 40 dB per decade instead of minus 20 dB per decade like in RC. So it gives you a second order filter, and order of microhenry will give you a much better time constant, or you can say your cutoff will be much lower. So now let's see if I can derive this V out equal to D times VDD. So let's go with this principle. So V equal to, so if this is plus minus VL, this is V out, so VL equal to L DIL by dt. So if I want to find the small signal current, what will be that? What will be the small signal current? So 1 over L VL times dt. Okay, correct. I am looking at a small signal, so if I look at delta component only, so I write delta IL equal to 1 over L VL dt. So during T on, your delta IL will be, what is the voltage across your inductor? VDD minus V out over L multiplied T on. So this is your current slope. Okay. So this is the slope at which your current will rise, and depending upon for how long it is on, that will define your peak. During off time, minus V out over VL into T off, correct. And wait, just fix it. So this one delta IL, can I write like this? VDD 1 minus D D over L. Okay. So you take VDD common, V out by VDD is nothing but D duty cycle, and T on is duty cycle times TSW. Okay. And this one can be written as over L into 1 minus D, correct, because T on plus T off over T is nothing but it's a 1, so you just break that. So your d on the T off will be 1 minus d times TSW if T on is d times TSW. Now, if you replace this V out by d times VDD, the ripple amount, the peak current will remain same in both the cases. Okay. So, whether you use this formula using V out or using V in, ultimately your delta IL or peak to peak ripple current would remain same. So, if you want to draw the current waveform, if this is going 0 to VDD, if this is your PWM signal, then your IL or inductor current will look like this. And this will be nothing but IL DC. So, what you have, and this is your delta IL. So, your inductor current consists of IL DC plus delta IL, and IL DC is nothing but I load. Okay. So, your average current, inductor average current will be same as your load current if your output is constant. So, in the steady state, your inductor current will settle to I load and output will settle to D times VDD.